convolution of two functions plus norm. So what we want to see is, because we have constraints like positive density, which means what? Which means you cannot have negative density of matter. It's not physical, you cannot have this. So but when you use Fourier, Fourier gives you negative values for the density. So it's not physical. Will machine learning help us in obtaining physical results? Here is the first try we did. All of this code, as I will show later, was done using Python. This is a plot that was done using asymptote. And so here you have in red the true density. In blue you have the neural network reconstruction. ANN means artificial neural network. And in black dots you have the Fourier reconstruction. This Fourier reconstruction was done manually because I know the density, so I tried to fiddle with the Fourier parameters until I obtained something that was the closest to reality. But these oscillations is the best that Fourier can give you. So the advantages of ANN is that they are easy to parallelize. So I will show you how we parallelize the code. And we do all this using Python and some specialized libraries that work with Python and CUDA because we use convenient cards. And the good thing with the ANNs is that once an artificial neural network is trained, it's very fast to compute the solution. You just do some matrix computations. Matrix, typically matrix times vector, so it's very straightforward. Now this is again the equation, and these are examples that we give. These are artificial examples. In imaging we call these phantoms. So we build phantoms using shapes that we know correspond to the real shape. Now these shapes were built are called quasi-splines. They're not really splines because you do not have the continuity conditions on different parts of the curve. So they're called quasi-splines. And to build these splines we use PyLab library, and this comes with Python. Mainly when we do development we use Python. We just hack and explore everything we can, and when we really understand what is happening, we then move to literal programming. I will show you how we use it. So what's a neural network basically? So a neural network here is the propagation of the signal. So the input would be the EPR spectrum, what nature gives you. Here are the computational neurons, and here is the output neuron. So we use a particular network that was proposed by David McCabe, who works at Cambridge, which means we have input is the spectrum, and you would expect here to have the density. So why do we have only one neuron? Because the network actually builds the density point on point. So this is why we have a single neuron here. So these are called hidden neurons. These are the computational neurons. So this is the first neural network we used that gave the result I showed you earlier. It was very nice, very good. But we wanted to improve on that because the phantoms we used at the time were very simple phantoms, and we'd like the new network to work on complex phantoms like the quasi-splines. So if you now write down the equations for a neural network, it's not written in many places, but basically a neural network is a machine that computes matrices times vectors. So this is very important because if you use a neural network with a few neurons, then you don't care if it's a matrix vector computation. You can do any kind of loops, anything will work because you have so few neurons that the computation goes very fast. But it's not possible to do this anymore when you have millions, when you have large data sets you want to go with. So you want to optimize. And the first thing you think about to optimize is parallelization. And the first thing you have to do when you want to parallelize your code is to first look, is it possible to write this as a matrix vector computation? Where are the matrices? Where are the vectors? Maybe where are the tensors? The tensor is a more than two-dimensional matrix. So this is the basic function of a neural network. this is what we need to do the parallelization. Matrix computation and a mapping. And a mapping, of course, is very easy to parallelize because a mapping is independent of all the elements. It's independent. So what we use now for deconvolution is a particular kind of neural network called a reservoir network. It belongs to the paradigm of reservoir computing. So you have an input here, which is what nature gives you, and the output, which is a single point in the density. And here you have the shadow for the order dimensions. Because what we use, in fact, is a reservoir with an architecture called fly-eye architecture. So if you look, I will show you a picture of a fly-eye afterwards. So if you now move from the artistic view of the brain and the reservoir to the schematic, what you're going to use to make the code, then you see here that you have a sparse random directed graph, which has to have special properties, and these properties are studied using a Python library called Network X. And then using this library, we characterize the graph, the directed graph that we built, and we make sure that it has the right properties. So here you have the input neurons. Here you have the matrix that in fact codes the input to the brain. So reservoir is based on a great idea. It was this recent paradigm developed in 2006. And what we do in this paradigm is that you have this random network that imitates the brain, random connections, sparse. And here you have the output neurons. And contrary to the previous networks I showed you, you only change those weights during learning. You never touch those weights here. The weights here are given. They never change. What you change is this. So once you have this network, what you need is to write down what you do with reservoir using matrix vector computation. As I told you earlier, if you're able to write what you do using matrices and vectors, then you can do anything. So let's try to write down what the problem is and how it can be written in matrix vector, and then we map this inside the reservoir. So back again to the equation, what you do is you do a discretization of the integral. So as I said in the talk, I expect you know what it means to discretize an integral. You basically discretize this discretization I write here is a simple collocation discretization. And you then arrive to the matrix equation. And here what we want to do is to inverse this equation. And what we want to do is inverse C. But the problem with C is that it's ill-conditioned, which means that if you have slight variations on R, then there will be massive differences in S. So it's ill-conditioned. So what does the network actually do? Well, the network is actually inversing this equation, but using an activation function, which is nonlinear. So what is this activation function? Once you have computed the neurons, you apply F to each neuron. As I told you earlier, there is a mapping. This is where the mapping comes in, and where the magic comes in. This function here is nonlinear. And what you do is you hope that the network is able to build the inverse of the matrix by reservoir magic. Because basically there are many conjectures on the workings of the reservoir, but no theorems. There are a few theorems, but many conjectures. So it's actually a field in which some mathematicians work, because we don't really understand the whole workings of the reservoir. We only know that it works at least as well as regular networks in a much shorter time. So, once you have understood this, you need to optimize the network. As I told you, the network here is random, but it never changes. So, how do you know that you have found the right network? Well, you need to explore many kinds of networks. So, you need to do some kind of optimization. So, you need to optimize the reservoir weights, but there can be many local minima. How do you know that you find the global minimum? I'm trying to show you the animation. So here is a small animation. So yes. Okay. So what's happening here? You have a function here. You have many local minima, and you have only a single global minimum. It's at the center here. So how do you manage to find the global minimum? Well, we use a technique called swarm optimization coupled to a genetic algorithm. So here you have a swarm here that evolves in time, and each of these particles goes to a new place by genetic variation, and we minimize locally, and we find the local minimum. And then we compare what the different particles have obtained as minimum. And if a particle is better than another one, it calls the other one, like in a swarm. And using this, you see that in the end, you have a very fast convergence to the global minimum, even though you start from very far away. So this is another function that is used for testing global minimizers. It's called the Fox-Hole function, because it's very flat, and you only have a few holes. And the real minimum is here. You see that I start with a very few particles, and none of the particles is in the global minimum. But then, thanks to this swarm optimization, I find the global minimum. So here is another example, but in this example, you will see that the particles do not converge to the global minimum. See? Of course, the algorithm can fail, as it's not fail-safe. So what you want to do is to make sure that you generate many minimizers, many global minimizers, and you hope that among all the many minimizers, one of them will find the true global minimum. Okay? I like to watch these videos. You see the swarm converging, it works like magic, and the algorithm behind is very simple. This code was written using EuroPython, using the PyLab library, and it runs very fast. One day I learned about the algorithm. At the end of the day, I had these pictures, and I was happy, and I knew I was on my way to finding the global minimum. So here is another big function. You have many local minima, many maxima, and you try to find the real minimum, which is here. So sometimes the convergence can be very slow, so you need a long time. You need many iterations. So this is why you have to parallelize the code, otherwise it's no hope. So you have to understand one thing, is that many techniques that were developed a long time ago could not be applied a long time ago because there was no computational resource to make the algorithm work. But now we do have the computational resources to make special algorithms, heuristic algorithms work. So you need to find a global minimum. this is the picture of the global minimum. You have many particles that are launched in different parts in parameter space. Then when they arrive on the top of the hill, they climb down and they find their local minimum. And they say, that's my quality. My quality is my local minimum. And then I use it and I genetically cross over with others. And the genetic crossover that happens actually happens on the sparse random network weight. So the genes on the network weight. So the three main algorithms we use are the reservoir computing or the fly-high architecture. Then we use the particle swarm optimization, and then the genetic crossover to make the swarm move. How does the swarm move, and how does it mix up? How does it genetically mix up? Of course, these algorithms can only work if you parallelize them, and the workhorse today for parallelization are GPUs. Then, in the end, after this, I will show you the software and the hardware architecture we use. In the end, once you have many candidates, how do you choose among all the candidates? So we use a particular technique that imitates what Watson does to Watson. It just beats human participants in a game called Jeopardy. Jeopardy is a game that is based on things like what's the size of Italy, okay, that's easy for a computer, and other questions which are based on wordplay, ambiguous meanings. So, and that game, Watson just beat the crap out of the best humans that ever played at Jeopardy. So what Watson does is that it has many algorithms, all the algorithms select a candidate answer, and then if one answer has a probability higher than 50% of being true, then Watson votes. Okay? If it's lower than 50%, it doesn't vote. So we actually developed something similar. In the end, we have many candidates. For all the iFly architecture, we have candidates that claim they have the right answer. Then we have what we call the possibility estimate. It's not the probability. It has nothing, it has to do with probability, but it's called the theory of possibilities. It's not the theory of probability. And so we use the theory of possibilities to build a matrix. And in this matrix, we select the one that has a possibility higher than 0.5. And to do that, we have a very large matrix. It's very large, and we want to find the lowest in all the lines. And for that, we use the argmin function, which is called the parallel row reduction. Because you have this big matrix, and you want to find the minimum on all the lines, so you want to reduce the matrix to a single column. This is called argmin, and you have very good row reduction functions that work on the QDA library. Are linked to Python. So it's very easy to test. Okay, so this is the fly eye here. So you see an eye here, which is made of many cells called, each cell is called a mycelium. And all of these cells are here. Each of these cells specializes in the reconstruction of a single point in the density. Of course, all of these are computed in parallel. When we want to parallelize, we have to be obsessed with matrices and vectors. Just only think about this. Where are the matrices? Where are the vectors? Where are the mappings? Where are the reductions? If you find these, it's good. And for that, we use the library called PyQDA. Python QDA is a wrapping around the QDA library. Very easy. You have to think that I'm not a professional programmer, so I want something that works easily. And PyQDA is just fantastic because you can test all of these IDs in a few days. Otherwise, I remember when I first looked at GPUs a long time ago, you had to look at the assembly code for GPUs and stuff like that. It was just hard. And for me, I couldn't work on it. It's not possible for me. So then when this came out with the corresponding cards, GPU cards, it was just fantastic. So here is just a fast summary of what we do and all the algorithms. And in each step here that you see, everything we do, Python intervenes. Python libraries, and sometimes in very small places you have little codes written in C. But the code written in C is in fact wrapped inside Python. It's called a kernel, a C kernel, and it's useful to have a little C kernel when you do not have an existing function that does what you want to do. So sometimes I'm obliged to write a few lines of C, but when I write those few lines, it's nice C, because it's C when it's useful. It's not C when you have to do things which are, everywhere, which frightens me. So it's just C when you have loops, simple things, good things for people like me who are not expert programmers. So this is general algorithm. So now, literate programming. All of this, if you look at this big algorithm, it's very big for a single brain. So in HPU for Science, there's a little core team with about 5 people working on it, with a few people working on the general framework for hardware and stuff like that, but we only have 3 people programming. So these people have to have everything in the brain. And to hold everything like this in one single brain, it's not easy. So we have to help ourselves with a programming paradigm called literate programming. This I discovered with Donald Knuth, who's a very famous programmer. Explain anything to you. So Donald Knuth wrote about literate programming. The main thing is the programmer strives for a program that is comprehensible because its concepts have been introduced in an order that is best for human understanding. So what does it mean? What does it mean? It's good. It's good for. It's very good for scientific applications because when you do scientific investigations, you start where you can. It's a very stupid sentence, but that's what you actually do. So you start with the first idea that comes to you. And that's how literate programming works. You start to write the code as it comes to you. Oh, I have to do this. And then maybe I have to import some library. Let's import it now. And then you just do it as you like. So what does it look like? This is a code developed literate programming. It's 3 lines. It's a kernel. It's a C kernel. Just to do some simple vector addition. Very simple, very straightforward. So what you have to remember is that when you use a GPU, the very nice thing is that all the cores in the GPU do the same thing, except that their index changes. They have an address, which is in the thread idx.x, that changes. So it's very simple. When we do vector addition, I will be the column position, and that will be mapped to the core number. So it's very easy once you understand that. So how do you write this in literate programming? Okay, this is simple. For people who know basic maths, this is simple. Just for the sake of the argument, how do you program this in literate programming? Because this is easy, but once it's written, you just forget about it. You're not very proud of this. It's very easy. Let's get proud of what we do. Let's do something that we can show to the other people and say, "Oh, that looks good." Okay, so these 2 pages correspond to the literate program that is equivalent to those 3 lines. Okay, I have added lots of stuff in it, and it's very nice. So what it does here is that I'm explaining the code to someone who is not even an undergrad, who comes from high school, who doesn't have good memories of how vectors work. So I just explain to them what a vector is, basically. And then I explain a vector addition. Okay. Very simply. And then I say, so if you want to add those vectors, let's write the vectors as ui plus vi. This is where the code comes in. There is no import, no function, argument, declaration, nothing. You just write the code when it's useful for the presentation. Then you continue and you say, oh, did I define I? What's I? Oh, I is the position in the vector. It corresponds to the thread IDX. Let's go in the documentation. There's thread IDX. So this is the definition for the thread. And then, it's C, so I have to declare the function, declare the argument, declare the type. Let's do it now. Because this is not as funny as what we did before. We can do it now. So we just split the code, in an order that fit the presentation. Once you do this, you obtain the final code that I showed you earlier. And for that, to obtain this code, you use a program called NoWeb, which is an adaptation of a program written by Knuth called Web. And that inside we have two sub-functions called no tangle and no weave. No tangle builds the code, and no weave builds the documentation. So that's the code built by no tangle, and that's the documentation built by no weave. So literate programming, just to go a little further in the argument, is here to help you reduce the complexity. When I read the archives, there's a very nice archive with the handwritten notes of Dijkstra on the web. It's very nice to read all this. Sometimes it's funny. He's a very, very tough guy. He's not very nice always, and it's very interesting to read, and he has a very nice handwriting. So Dijkstra says, I hope that in the future, languages should deepen our understanding of the processes of design and creation. It should give us better control over the task of organizing our thoughts. It should help us, because programs are big, it should reduce complexity. And apart from literate programming, we also use a programming paradigm called reproducible computational research. It was proposed by many people, including David Donohoe, who is a big guy in signal analysis. And David Donohoe said that, a traditional scientific publication is incapable of finding and rooting out errors in scientific computation. Reproducible computational research in which the full computational environment that produces a result is published along with the article. So you see, you publish an article, you publish the figures, and you have the code for the figures, you have the data, and you have the code that did the analysis of the data. All of this comes online, so anyone can check what happened. So now let's go to the software. So for the software, we use Linux operating system and ext4 for the root system and for the operating system in general. And for storage, we use BTRFS. That's a very personal choice because first I found BTRFS very cool. When you're not a professional programmer, you're a little geek. Okay? So you try to find things that you find cool. I found BTRFS very cool. And it turns out it was also usable. So I made the choice for BTRFS, but BTRFS has defects when you try to move data. If you move lots of data around, you can have data corruption. Things get weird. But we don't move data. We store it, we read it. We don't move it. So BTRFS, in this kind of usage we have, is very nice. You just do RAID 0, very fast, a single line, and it has a very Git feeling. Because we use Git for versioning, it looks a bit like this, and I really like the feeling of using BTRFS. For development, we use an editor. It happens we use Vim. You could use the Emacs also. Python for the language. PyQt for the main Python library to work on GPUs. We use scikit, and we use the library we discovered recently called CUV. Very powerful library. It's based on C++ templates. Very nice. We also use C for the little kernels, and we use Cython. Cython is magic. I will show you a little example of Cython, Cython is coupled with Sage. Very nice, beautiful. For the literate programming, we use NoWeb, which has two sub-functions called NoTangle and NoWeave. For the data analysis, we use scientific Python, IPython, Sage, which is just marvelous. We are replacing Mathematica with Sage. It's very nice, and it has LaTeX built in. And we use MinerVI for 3D imaging, display. We use Asymptote for many schematics. And we use Google Docs for collaboration. It's a fantastic tool, Google Docs. Just amazing. You can work simultaneously on the documents. It's just marvelous. The only defect it has is that it doesn't work so well with LaTeX. So you have to have those PNG images that you plug in, but sometimes you just write because you don't have time to do anything. But it's really nice. So if Google could work on the LaTeX, the very nice LaTeX, it has little LaTeX if you write the documents. It doesn't look like. So how does Cython work? Here is a very simple example based on Monte Carlo integration. Monte Carlo integration, if you don't know about it, just read it on Wikipedia. It's just beautiful, breathtaking, very simple. Developed by Norman and Pullman among his friends. It's just beautiful. So here is a one-liner for little Monte Carlo integrator, very simple. And here is the Python equivalent, using loops. So what you do when you use Python is that, first of all, you hack a line, because it's always nice to have a single liner. Okay? Then you write a loop, because that's how the world is, it uses loops. And then, once you have the loop, you just siphonize the code. Siphonize, I call siphonize, is just typing. You type the variable. Here, if you look at the differences, you have a cdef to define f. So cdef means that the function is only available to the C. It's not exposed to Python. You will not be able to use f in the Python environment, but it's faster. And then you define the siphon function, which is just a typed version of the Python function. So how we work is we write the Python code, and when it works slowly, then we siphonize it. Very simple. So the system limits, as I told you, because you don't have in high-performance computing there's rules. If you just something which is quite amazing, the CERN produces 1 gigabyte of data each second, and all this is dealt with a network of 100,000 computers. So if it's good for them, it's good for us. BTRFS, I told you about it, and ext4 because you need something very stable for your OS to move down. This is an example of Python. These are the 3 functions I told you about, and how much time you gain. You start with 11 seconds for classical Python, and you go to 0.12 seconds, just a factor multiple. Just in one go. No thinking, just type the values. For the Git, we use a flowchart that was proposed on the web by Vincent Gleason. It's a beautiful flowchart. We have different branches, it's nicely, very nice. I really advise you to look at his page. It's all described, very nice. Beautiful. So we have the repo. It's not centralized, but it is centralized. You read on his page when he needs like this. So now to the hardware. So we do everything from the algorithms to choosing the software to coding to building the cluster and everything. So what do we use for the cluster? So here's the little cluster we have. So we have one computer called the master that centralizes data. It frames the calculations. It gives the orders to the workers. But the workers do not receive orders. They ask for orders. We have 6 workers from 3 to 7 GPUs, and we call an HPU a hardware CPU thread and a GPU processor. That's what we call an HPU. One thread, one GPU. And all the HPUs run the same algorithm, except that we change the part of parameter space we explore. So that was the beginning. When I sent that picture to a friend, it was last Christmas, he said, well, that's good, but it looks like Frankenstein. Okay? So now it looks a little nicer, and we have a hardware engineer who is not specialized in computer, because he works in the chemistry lab, of course, who helped us set up the cluster in a nice way. Of course, we use GPU cards, 4 different cards, which correspond to 2 different GPU processors. We started some time ago with GTX 285, and then we end now with the GTX 590, which is a dual GPU card. Beautiful. So this is the master. It's a dual Xeon, 24 gigabytes of memory. It has 5 RAID 0 SSDs for data management, fast storage when it receives data from the workers. We have 20 terabytes of storage, long-term storage, no SSD, just normal hard disks. And this is the worker 3, and here we can see the 4 cards will come together, the 4 580s. But in order for the 4 580s to work together like this, we have to really think about the choices we make. In particular, we have to think about the motherboard, because the motherboard has to have enough PCI lanes in order to have maximum bandwidth when communicating with the processor. So in this card, we have 64 PCI lanes. So this means we have 4 16 times video cards. It's 4 times 16. Okay. So it works. Very nice motherboard, but we just, I think we bought a few months ago, we bought the last 3 that were available. In fact, we have more now. But it's very hard to have this kind of hardware. Very difficult. Many people use video cards, motherboards in which they don't have enough PCI lanes. So this means that one of the GPUs will not communicate at maximum bandwidth with the processor. So you lose time. You lose very important time. The Worker 5 is the latest that actually works, because we have a Worker 6, but it's not working at this point. So the Worker 5 uses 3 590s, this means 6 GPUs and 1 580, 1 GPU, so that makes a total of 7 GPUs in a single box. So that's the maximum, because we really designed the box so that it worked, and that the power consumption corresponded to the cards. It was a very long one. It didn't work at the start. It's not, plug it. The problems we had with temperatures. Temperature was very high sometimes, so we had to use special risers. We ordered very high bandwidth risers to have the cards outside the box. We sometimes had electric overconsumption, so we needed to really measure the consumption. And many defective components. It actually happens that in game hardware, if you buy 1 card, okay, but if you buy 10 cards, then the probability adds up, and you find a defective component. So that was a big problem, but the hardware manufacturers actually, send them back the hardware and they send it back. But it's always painful to lose time. And to make the test, it doesn't work, you're not happy. The temperature typically rises to about 90 degrees in a single card. We have a distributed architecture, completely distributed. All the workers are independent, which means that we can have a worker which is far away, and it will contribute in the same way as the local workers. So the software components for non-computational cluster activity. The data storage is homemade Python dictionaries using C people. Very nice. We don't have, we have data, but it's stored. We know how we want to interrogate the database, so it's handmade and it's homemade. We use Carrigale. It's a very nice web server built in Python. Very nice. So we use it to make data requests and visualization from cluster. Hence the cluster working and everything. Communication is made using the multiprocessing library module. We use client server. And we have a tool to give us instant snapshots of the cluster activity. If you compare HPU for science with Watson, 30,000 euros for HPU for science. Watson cost about $22 million. The power 35 teraflops peak, which means that in reality we reach 16 teraflops. 18 teraflops, 1,170 megaflops per euro, 4 megaflops per euro. Storage 20 terabyte foot. I cheated a bit because these 20 terabytes, you actually have 15 terabytes of RAM. I only have 48, 60 gigabytes of RAM. So the short-term evolution is to test OpenCL with PyOpenCL. Apparently I went to a specialized seminar. It's a little more painful to program in OpenCL. So because I'm not a professional programmer, maybe I'll stick to IQ. Open source the code, of course, it's the whole thing of reproducible computational research. And move to the new cards, which speed will be twice as fast as the previous 590s. Very nice. And of course, this machine learning application for deconvolution will not be the only application of the machine learning machine we have. And we also program lots of other applications in chemistry. The thing is, we like to stay in the lab where the questions arise. If you separate from the chemistry lab, then you develop your own questions, and then you get disconnected from reality. So we like to stay in the chemistry lab. So this is final drawing. Here is the oracle, the perfect neural network, and you have the little brains trying to find the oracle. So maybe Python help us find the oracle. Team and website.
question?
Right, I assume you're using Cython for some of the high performance stuff. How are you using PyPython? Because they've gained very impressive performance gains.
Yeah, we make the choice of cycling. We never tried that. I mean, we could.
Anybody else? Okay, thank you, Yann.